Nuclear chemistry. What's it all about? Well, as the name suggests, it says something about the nucleus of an atom. Remember, atoms are made of protons, neutrons, and electrons. And of course, the nucleus just has the protons and the neutrons in it. When those are manipulated and we increase or decrease that ratio or the numbers inside, that's what nuclear chemistry is. Now, what makes an atom stable? The atomic number, or the number of protons, is noted by the letter Z. The mass number, or the sum of the protons and the neutrons, is A. A shorthand way to write a compound, or element, is by this formula, AZ over X. Now, it's not really a formula, but it's just a way to show something. So, for example, if I had carbon, and carbon with a mass of 12, it would be written this way. Sometimes it would be written carbon with a dash 12, or sometimes we can just say carbon 12. In other words, there might be different isotopes of carbon, as we know. This carbon has a mass of 12. It also has 6 protons. Here's another isotope of carbon. This is carbon 14. It has 2 more protons, but this is how it would be written. So this is just a shorthand way to write this. I think we've talked about this before. So when the nucleus of the atom is unstable and it breaks down, this leads to what we call radioactive decay. What makes a nucleus stable or unstable? Well, when a nucleus is unstable, it does undergo decomposition. Why does it do that? It tries to form something more stable, or a different nucleus. Nucleides, that means those things in the middle, the nucleus, with 84 or more protons are unstable. So if we look back here at the periodic table, and we see the heavier atoms, these are the ones that tend to be unstable. You will see later it has to do with the ratio between protons and neutrons in the nucleus. Light nucleides are stable when Z equals A minus Z. In other words, when you have the same number of protons and the same number of neutrons, then things tend to be stable. As in carbon 12, which is this one, you can see it has 12 things in the nucleus, but 6 protons, 6 neutrons, and 6 electrons. Now we really don't care about the electrons because of course they're on the outside of the atom, but carbon 12 has the same number of protons and neutrons. This happens to be a stable isotope of carbon, whereas carbon 14 is an unstable isotope because it has more protons than neutrons. And when you have more things in the nucleus of the atom, they tend to be more stable, or the neutron-proton ratio is not 1 to 1. For heavier elements, the neutron-proton ratio required for stability is greater than 1 and increases with Z. Certain combinations of protons and neutrons seem to confer special stability. Even numbers of protons and neutrons are more stable than those with odd numbers. So that's why carbon 12 is more stable. Certain specific numbers of protons or neutrons produce especially stable nucleides. That means that which is in the nucleus, like a 2, 8, 20, 28, 50, 82, and 126. Excuse me. You can see from this chart, which you can find in your book, there is a zone of stability. In other words, looking at that ratio, if it falls along the red pathway, that tends to be the zone of stability. And for the smaller atoms, the 1-to-1 ratio tends to hold, and as the atoms get heavier, the zone of stability changes a bit. But that's just a shorthand way to think about it. There are different types of radioactive decay. Now, you might have heard of radiation. if you know someone who has undergone radiation treatments for cancer, for example, that is a form of radiation that's given specifically to people who need treatment because they want to try to kill growing cancer cells. So radiation treatment is forceful application of radiation to a specific part of the body. So if you have a tumor, they will give radiation to that tumor. They don't radiate your entire body, they just radiate the section of the body with the tumor. You may know people who have undergone chemotherapy. That's chemical therapy, where you actually get some intravenous or oral medication to try to cure the cancer. Again, kill the cancer, fast-growing cancer cells, and keep the person alive. But radioactive decay is a part of this process. There's a special kind of radiation that's given to that person to kill those fast-growing cancer cells. What are those different types of radioactive decay? Well, alpha production is probably the easiest kind of radioactive decay. It's certainly the most, the least penetrating, let's say, and less dangerous. It's actually a helium nucleus. It's very common for heavy radioactive isotopes to produce alpha particles. Something like uranium, which we would use in a nuclear power plant, would undergo radioactive decay by producing an alpha particle. You can see here in this example, this is the alpha particle. And you do need to know that alpha is a helium nucleus, or 4,2He, 4,2 helium with a mass of 4. So sometimes these easy equations are given because they want to show you how to write these nuclear equations. Here's the example of uranium with a mass of 238 undergoing alpha decay, as it would be called. You notice one of the particles is the alpha particle, and then it also produces thorium-234. How do I get that number? Pretty easily, because you can see that if we add 4 and 234, we get 238. And if we add 2 and 90, we get 92. We have to make sure the sum of the atomic masses in the top equal each other on both sides of the arrow, and the atomic numbers on the bottom also add to produce, in this case, 92. So it's very easy to figure out the missing piece here. Some kinds of questions you might notice on the exam, perfect multiple choice question, it could say uranium-238 undergoes alpha decay. What is the identity of the other product produced in this reaction? And in this case, thorium-234 would be the answer. Another kind of decay is beta production. Both of these kinds of productions can be produced along with other more penetrating types of decay. If we have alpha radiation, let's say something is naturally occurring in the earth, which happens, uranium is in the ground, and it produces alpha particles. It isn't so bad because it can't really penetrate in your house, for example, from the outside into the house, because you have walls and windows, and you're wearing clothing, I hope so. So if I have some alpha radiation coming towards me, as long as I have my clothes on, I'm fine, because it can't penetrate. Beta production is a little bit more penetrating, meaning if beta particles are produced and I have my walls and windows closed, then that would stop beta radiation from entering my house. Now, what if it's already in there? That's a whole other question. What is beta production? Here's an example of thorium-234 undergoing beta production. Beta production is essentially the effect of changing a neutron to a proton. And you can see here 0 minus 1e, it's like an electron or beta particle, is being produced. You can see that this reaction is one that took the alpha production from uranium-238, then thorium-234 was produced, and then it continued to break down, and you'll notice it produced Pa-234 with atomic number 91. So that's what I mean when I said it's the effect of changing a neutron to a proton, because the number of protons have increased by 1. That's beta production. Other types of radioactive decay, gamma radiation. Gamma rays refers to high energy photons. Frequently, gamma radiation production accompanies nuclear decay and particle reactions. So when you're thinking about radiation treatments, this is what you're thinking about. Gamma radiation. This is penetrating the skin. A nuclear bomb would produce gamma radiation and kill fast-growing cells, and people, certainly the closer you are to that source, the more likely you are going to be affected. Of course, there are studies now for people who have been exposed to gamma radiation over time, and their development of cancers and things like that as a result of this gamma radiation earlier in their life. So gamma radiation can change cellular structure, which is the fear, of course. Let's look at an example of gamma radiation production. Here we have uranium-238. You can see it produces the alpha particle that we saw earlier, and it produces 2 gamma rays. The emission of the 2 gamma rays is one way a nucleus with excess energy in the excited state can relax back to its ground state, and that's actually what's happening here. You'll notice it doesn't have any mass and it doesn't have any charge, so it's often, at least initially, was difficult to detect. So that is gamma radiation. Other kinds of radioactive decay, positron production. For smaller atoms, it's the opposite of electron emission. Let's see an example of it. Here's sodium, and it's producing a positron. Notice it's also an antiparticle. It's the net effect is a change. It's changing a proton to a neutron, which is the opposite of the beta decay, which we saw before. It's an antiparticle of the electron because antiparticle, when they collide, they cancel each other out because they're opposite. So this is the result of this one. So we can actually change one atom of sodium into another atom of neon with this positron production. So that could happen. Electron capture is another example. One of the inner orbital electrons is captured by the nucleus. It's actually pulled in. And so here we have mercury becoming gold. This is just like the alchemists back in the Middle Ages. They wanted to turn things into gold. If they only had the right nuclear background and had a particle accelerator and all kinds of fancy equipment, they could have actually turned mercury into gold. And you can see this is how it is done. It's actually added to it by a particle accelerator, which you can see in your textbook, and then gold is produced. Also notice gamma radiation is a result of that as well. So what is a decay series? Well, when one atom, like uranium-238, that's this one up here, the one that produced alpha particles originally, undergoes a series of alpha and beta decay. You can see they're showing alpha decay, then beta, then alpha, then alpha, then alpha, etc., and moving back. Eventually, it becomes stable down here. It becomes lead-206. Uranium has, or any unstable nucleus, has a desire to become stable, and over time, it breaks down and it becomes stable through a series of reactions. The decay series is that series of steps, almost like a mechanism that this atom goes through to become stable, and eventually it becomes lead-206. So let's look at this example. Which of the following produces a beta particle? All right, so this is very easy. It's just testing your knowledge of, do you know what a beta particle is, and which one is it? Hopefully you saw it. That was this one. I see a beta up here in letter A, but it's not producing a beta particle. That's electron capture. The next one is a positron, and of course letter C is an alpha particle. So letter D is the only one that produced a beta particle. Rate of decay. Rate of decay is equal to K, some value of K, times N. It's proportional to the number of nuclides. This represents a first-order process. We already talked about half-life, so here again we're going to look at half-life. It's the time required for the value of nuclides to reach half the original value. So if we have a 100 gram sample, it's the time it takes for half of it to become stable, or half of it to remain radioactive, so 50 grams. The half-life for first-order reactions is listed here. And earlier, remember, we talked about order of reactions from integrated rate law, and I think this was also listed on that page, which is very helpful in that particular chapter. Okay, so let's look at an example of radioactive decay. If you start with 64 grams of material with a half-life of 10 years, how much will be left after 40 years? Well, we can do it one of several ways. I'm going to move this a little bit so I can write better. So you're looking at the ceiling, I think, so I apologize for that. If we start with 64 grams of material, then after one half-life, 32 grams would be left, and that would be 10 years. And then after another 10 years, we'd have 16 grams. And then after another 10 years, we'd have 8 grams. And after another 10 years, which by the way is the 40 years we're looking for, we'd have 4 grams left that were radioactive. That's the probably easiest way to do it. So if there's a question like this, and you can just do simple math like this, just continue to divide by 2, then that would be fine. Most of the problems you might encounter might not be that simple. So you can use the formula NT equals N naught 1/2 to the N. And we can plug in and get 64. That's the initial. 1/2 to the, in this case, number of half-lives that have passed. There are 4 half-lives that have passed. And then you should figure out the answer, which in this case is 4 grams. Now, here's a question I typed earlier, and I see a typo in it, so let me fix it. It should say iodine, not IOD, or iodine. Iodine 131 has a half-life of 8.07 days. A lab worker discovers that a sample of iodine 131 has been sitting on a shelf for 7 days. What fraction of the original nuclei is present after 7 days? So some of the nuclei, of course, has broken down. Let's think about it too. If the half-life is about 8 days, and we haven't reached 8 days, then it's going to be less than half that has broken down. So when we get an answer here, the answer here should be greater than 50%, because if it was 8.07 days exactly, we would have 50% of the original nuclei that would be present. And the other 50% would have broken down and become something else. So let's look how to do this particular question. All right, so let's use this formula. And from our earlier discussion of half-life and order of reactions, we're going to use this formula, log NT over N naught equals minus KT over 2.303. We don't know K, so we actually can substitute K, remember, as 0.693 over T half. That's the half-life formula from earlier. So I can replace that, and I could get log of NT over N naught equals negative 0.693 T over 2.303 T half. So plugging in, whoops, let me go back. Come on. I'm going to find it. Nope, that's the wrong way. There we go. So plugging in the information that I have, I can have negative 0.6937, because it's originally time of 7 days has passed, and 2.303, the half-life is 8.07 days. When we do that, I get 0.2610. So nt to the n over n naught equals 10, taking the log of both sides, to the negative 0.2610. When we work it out, we get 0.548, which is, in percentages, about 55% of the sample. So it makes sense that a little more than half is still active because we haven't reached its first half-life yet. We could also substitute into the ln nt over n naught equals minus kt formula, and we could substitute in and we'd still get about 55%, raising e to the x. So either way you should get about 55%. And the last example that we're going to look at is if a 0.001 gram sample of technetium-99 has a decay rate of 6.3 times 10 to the 5 nuclei seconds minus 1. What is the decay rate, or decay constant, I think is what I meant to say here. What is the half-life of technetium? So this is kind of two questions. Remember from earlier, the rate equals k times nt to the first. This is a first order reaction. So then k is rate over concentration of nt. And k is 6.3 times 10 to the fifth, that's the rate, over the number of nuclei, which in this case is 6.1. Well, I can't get that. I was about to get that, but I have to solve for it. So how do we get that? Well, we have to get it from this information here. We have a 0.001 gram sample. How many nuclei are there? Well, in 1 mole of technetium-99 has 99 grams, because that's its mass. There, in 1 mole sample, there are 6.02 times 10 to the 23 nucleides in that mole. And when we work it out, we get 6.1 times 10 to the 18 nucleides. And that's the number that I put in the denominator, or the nuclei. I should say nuclei, N-U-C-L-E-I. I've got too many L's and E's and I's. N-U-C-L-E-I. There we go. So when we solve, the k value I got was 1.0 times 10 to the negative 13, and that's seconds to the minus 1, first order reaction. What is the half-life of technetium? Well, we know the half-life formula, T1 half, is 0.693 over k. We know the k value, plugging in T1 half equals 0.693 over 1.0 times 10 to the negative 13, and when I solve, I get 6.9 times 10 to the 12 seconds. That's how many seconds, and obviously you could change that to minutes or hours or some other unit, but that is the idea with these formulas, being able to substitute in and solve for the missing piece.